Good evening everyone and welcome to my YouTube channel. So here today we are going to be looking at some static equilibrium problems, whereby we have problems in which objects are not moving. So we are going to look at these four problems. So what do we mean by static equilibrium? So just as I have said, when a body is under static equilibrium, it simply means to say it is not moving. Now the first condition for static equilibrium is that if you add up all the forces, the summation of the forces should be equal to 0. What we simply mean is that if, let's say, we have two forces, one force applying a 20 newtons this direction, the other force 20 newtons this direction, then what you are going to say is that since one is they are moving in opposite direction, that simply means to say one has to be negative. So that means to say the summation of forces here is equal to 0, because when you get one, let's say this one is taken to be positive and this one moving to the left is taken to be negative, it will be 20 minus 20, which is equal to 0. Now, which is true, if two forces are acting in opposite directions, then that simply means to say the force that will be produced is 0 newtons. Therefore, an object will not move under that condition. The second condition, which we are not going to more like answer problems for this video, but is the sum of the torque must not be equal to 0, which we are going to dive deeper. So here we say the summation of the torques should be equal to 0. We are going to deal with this in the next video. So let's answer those questions. So let's begin. So if we have these diagrams, we have a traffic light of mass 10 kg hangs from a cable tied to two other cables fastened to support as shown in figure 4.16. The upper cable makes an angle of 37 degrees and 53 degrees with the horizontal. If the system is in equilibrium, meaning to say it is not moving, finds the tension T1, T2 and T3. So this question, I think there was a misplacement in the values of T1 and T2. They should be interchanged. So now, how do you answer such problems? So never forgetting vectors. So this one, we are going to draw the Cartesian plane like that, the XOY plane. So if you draw the XOY plane, it would look like something like this. So according to the Cartesian plane, then what we have a force going in this direction. We have one going straight down. So we are going to say already it will be one going down like that, which is our T3. Then we have another one, it's looking like that. Let's change the color to add contrast. So this is what we have. Then we are having something like this on this side. So we are going to have a straight line like that. Yeah, so this is what we have. So just to extend this, now what we have here is that we have something like this. Then on top we have, it is looking like this. Then what we are going to do is identify the angle. So 53 is here, so we are going to put the 53 degrees here. Then here what we have is a 37 degrees like that. So if this is 37, already this is making a Z like that. So if this is 37, even here it will be a 37 degrees like that. So we have a 37 degrees. Even here it will be a 37. Sorry, not 37. We have 53 here. It means to say here it will be 53 degrees. Then what we are going to do is that we are going to do something like this. Extend this side so that we have something like that, just to add contrast. So this is what we have. So now this is where many students fail to just grasp the concept. So according to vectors, whatever is the opposite will assume the sign. So like for example, if you look at this, the angle 37 is here. So with reference to this angle 37, its opposite will be termed as your T. Now remember, this is your T1, so we are going to say if this is T1, so this one will be your T1 sine of the angle 37. So whatever is the opposite, then the base there will be your T1 cos of 37. So the angle, where the angle touches the line, that will be your T1 cos of whichever angle. Then likewise, even here, that is what we are going to do. The opposite side will be T2 sine of our 53 degrees, like that. Then at the bottom here, this one will be equal to the T2 cos of 53 degrees. So meaning to say the base, whichever angle is in contact there, is what we are going to call T2 cos of the angle theta. Now if you have one angle attached to some mass like that, then this mass will be a direct thing, because T3 shall be equal to whatever weight it is attached to. So if we have something attached to that, that will be your T3. So T3 is equal to the weight of this. So if we have the traffic light, if it is 10 kg, let's begin by answering what our T3 is. So we can say T3 is equal to the weight of the traffic light. Or if you want, you can say for T3, you can say summation of forces in the y direction is equal to 0. So it is in static equilibrium, meaning to say the traffic light is stationary, it's not moving. So we are going to say it is equal to 0, but this is in the y direction. So for this one, we can say T3 minus the weight. So if you subtract, because the tension is a force that more like pulls an object, it produces a pull like that. So if we have the weight of the object downwards like that, our mg, it means to say the tension will go up. So it will be T3 minus the weight is equal to 0. That means that the T3 is equal to that d. So each and every time you have one mass attached like that, then that's just your T3. So in this case, what we are going to have is that our T3 should be equal to, we know that the weight is equal to mg, the mass is 10 kg, then we multiply this by the gravity is 9.8 newtons per kg. So if we multiply this, we are going to find that our T3 is equal to 98 newtons. So tension is the force. We have calculated the tension there. Then when we calculate the tension there, we are now going to find our T2. So how do we find our T2? First, let's come up with equations that will help us. So as you can see, now the way it is, if T3 is equal to the weight, it means to say here we are going to consider the weights to just be acting down like that. So now what we are going to do is that we are going to say, so what we are going to have is, we are going to say now the summation of forces for the entire system of forces in the y should be equal to 0. Now tension, this tension number 3 was acting up with respect to this weight. But if we consider the whole system, the tension is acting downwards. We have the upwards, which are T2. So as you can see, these, the ones that are on the sides, they are acting up. So we are going to say our summation of forces in the y, since it is, as long as it's in static equilibrium, it shall always be equal to 0. So we are going to say, which forces are those? So these two forces are acting upwards, as we can see. So these two forces are acting upwards like that. So both of them. So we are going to add them up. So we are going to say T sine of 37, which is the angle on the side, plus the T, so this is our T1, plus T2 sine of the one on the other side is 53 degrees. So we are going to say 53 degrees minus the one that is acting in the downwards direction is T3. So we are going to say minus our T number 3 will be equal to 0 like that. Then what we are going to do is that we are going to move our T3 the other side, so that the equation becomes T1 sine of 37 degrees plus our T2 sine of 53 degrees should be equal to T3 like that. So our T3, so what we can do here is that we can evaluate the values. So the sine of 37 gives us a value of 0.602. Then it attached T1 like that. Then we have plus the sine of 53 on the other hand is giving us a value of 0.799 T2, which should be equal to our T3. We found it to be equal to 98 newtons. So we have two unknowns. In order for us to find the value of the two unknowns, we are going to call another equation. So now we have dealt with the summation of forces in the y. Now it is in static equilibrium, meaning to say it is not moving in all directions. So even in the x direction, we have the x direction like that. We are going to say summation of forces in the x as well. Summation of forces in the x should also be equal to 0 like that. So these forces, we have one force acting going in this direction is our T1 cos of 37. So they are going in opposite direction, therefore we must subtract them. So we have our T1 cos of our 37 degrees minus the T2 cos of our 53 degrees should be equal to our 0 like that. Then what we are going to do is that we are going to evaluate the value. So the cos of 37 gives us a value of 0.799 T1. Then we have minus cos of 53 is giving us a value of our 0.602 T2 like that, should be equal to 0 like that. Then what we are going to do is that let us take the negative the other side. Then we are going to have a 0.799 T1 should be equal to 0.602 T2 like that. Then what we are going to have is that we have this, let us divide by 0.799 so that we can remain with just T1, 0.799. This will give us a value of T1 should be equal to, we have, when we divide these two values, we are going to get a value of 0.753 T2. So this divided by this is 0.753 T2. So this is our T1. So what we are going to do is that we are going to replace where there is T1, you are going to put this value. Let's lift that equation. So what we are going to have is, so T1 is equal to this. So that means to say where you see T1, put this value. So we are going to have a 0.602 times our T1 is equal to this value 0.753 T2. Then we have plus 0.799 T2 should be equal to 98 like that. Then we are going to multiply 0.602 times 0.753. This is going to give us a value of a 0.453306 T2 plus our 0.799. Then we have our T2 should be equal to 98. Then what we are going to do is that let's add the two values. We are going to get a value of a 1.252306 should be T2. When we add these are like terms, T2 should be equal to 98. Then what we are going to do is let's divide this value. When we divide this, we are going to get a 0.52306. So we are going to get a T2 to be equal to 78.26 like that newtons. So this is the value that we have gotten, which they just rounded it off. Okay, so we have our T1. So this is where I was saying that they misplaced the letters. So this is supposed to be for T2, which is supposed to be at 78.2 like that. So this is the value that we have gotten. Then we are going to have, so this is our T2, then our T1. Getting the equation, we match the subject of the formula. So getting this equation, we are going to get a value of, so we have, so our T1 should be equal to 0.753 times our T2 is equal to 78.26 newtons. So multiplying these two, we are going to get 0.753. We are going to get a 58.93 newtons. So this is our T1, which is written as our 59 there. So they have written it as 59, which is basically the same thing. So we have answered that one. Let's move on to the next question. Let's look at our next problem. It says that the system in figure 11 is in equilibrium with the strings in the center exactly horizontal. Finds the tensions T1, T2, T3 and the angle. So we are going to do the same thing, but we are going to isolate this into two axes. So we are going to have one axis which is going to look like this. So we have one axis like that. So this is what we have. Then what we are going to do is that we are going to draw the two lines which will look like something like this. So as you can see, it's going in this direction, so we are going to do the same with that. Then also it is now going down like that. So this is what we have going down. Then it is also going in this direction like that. So this is what we have. So what we are going to do is that we are going to isolate it into two parts. So what we are going to have is, if we have the angle of 35 degrees here, so if this is 35 here, I'm just uplifting everything, and as you know this is the 90 degrees, then what we are going to have is that we can, to find the angle here, we can just subtract, since the theta that is here plus the 35 degrees will add up to 90. If you do your math, theta shall be equal to 55 degrees. So we are going to get the 55 and put it here. Then what we are going to have is a 55 degrees like that. Then we can now begin answering the problem for that part. So let's just also identify this other part. For this other one, what we have is the same diagram like that. Then what we are going to do is that we have, it is going in this direction, so we have something like this. Then we have the angle theta here. Now this angle already, the theta is here, so meaning to say if we say 90 divided by theta, we don't want to do that, but it's still okay. But due to the fact that we have theta, we don't know the value, so we are just going to leave it like that. Then down here, we have the down here, it is going down like that. Then we have the 50 newtons down. Here we have a 40 newtons down like that. Then what we are going to have is that we have our T2. We have our T2 like that. We have our T2. So T2 is common on both diagrams. So let's begin by resolving this first part. So we can choose to use 35 or 55. It's still okay, but since you are used with using the base, we can now say, since the opposite side is always the sign. So if we have T, this is our T what? If this is our T1, that means to say the opposite side will be T1 sine of 55 degrees using this angle. Then the base will be T1 sine of not sine, but the base will be the cos of 55 degrees. Then what we are going to have is that, let's also resolve so that you can understand something. Let us resolve here as well. So if we resolve this one, what we are going to have is that you should be very, very careful. So this is what the implications mean. So we are going to do this. So already the opposite side will be your sine, always the side opposite to the angle. That means to say the x1 will now be your sine, because it is the one that is opposite. So we are going to say if this is our t3, if this is our t3, we are going to say this is t3 sine of our theta, like that. But this is in the x. It doesn't matter. What matters is it opposite? If it is opposite to the angle, then it shall assume sine. That's the way it is. So then the side that is in contact with the angle is now what we are going to call t3 cos of theta. So this, if this is t3 cos of theta, that means to say even here it is t3 cos of theta, because this is in the y-axis. Even down here, that this means that these sides are equal. So this means to say even here it is t3 sine of theta. So this, the x-axis now has become t3 sine of theta, like that. So now what we are going to do is that, let us be able to answer. Let's first see how much we can answer with this one. So what we are going to have is that, let's say summation of forces in the y direction. Let's begin with the y, since we have a force already. So summation of forces in the y direction is equal to, we have a 0. Now the forces in the y are, for this isolated system, is for this one, this is the force that is going up, so it shall be our t1 sine of our 55 degrees, like that. Then we are going to, the force that is downwards is minus, we have the 40 newtons down, which is, if we have, let's say if we call this one as our tension, it will be equal to 40. So we can have minus 40 newtons should be equal to 0. Then what we are going to have is our t1 should be equal to, so t1 sine of 55 degrees should be equal to, if this goes that side, it will be 40, like that. Then divide by sine of 55 degrees, divide by sine of 55 degrees. So our t1 shall be equal to, if you divide this, we are going to get a value of 48.83 newtons, like that. So that means to say we have gotten this one. Then we are going now to say, for this isolated system, let's also now look for the x in the x direction. This is where x is where the t2 is. So we can use we can use the x to take advantage of this. So what we are going to have is that the summation of forces in the x direction is also equal to 0. Which forces are those? So we have this force is in the x direction, this one the base. So the base is the x direction. So we are going to say our t1 cos of our 55 degrees minus, we have our t2 should be equal to 0. Take the t2 the other side, so that, remember, these are going in opposite direction. This one is going this side, this one is going this side, because the resultant is going up there. It means to say even the x direction is in this direction. That's why we are subtracting them. They are going in different directions. So take the t2 that side, it will be t1 cos of our 55 degrees should be equal to our t2. So our t1 in this case is equal to, we have 48.83. So we have 48.83 times the cos of 55 degrees should be equal to our t2. Then when we multiply times our cos of 55, this will give us a value that is equivalent to 28.01 newtons is equal to t2. So we have found t1 and T2. So all we are remaining with is to find the angle, which is this theta, and T3. Then we are done. So let's take advantage of the values that we have found, because T2 is also found here, so we can take advantage of that. Let's lift this diagram. Now we can say summation of forces, let's begin with the y, is also equal to 0. So the one acting upwards in this case is our T3 sine cos of theta. As you can see, that's the one that is acting upwards. So we can say the T3, so we can say T3 cos of our angle theta minus the one acting downwards is our 20 newtons, 50 newtons. So we have 50 newtons should be equal to 0. Take the 50 the other side, it will be T3 cos of our theta should be equal to, we have our 50 like that. Then we don't know cos, we don't know theta, we don't know T3. So we are going to go for the summation of forces in the x. So the summation of forces in the x is equal to 0. Which forces are those? There is the force that is pulling in this direction, and this force is our T3 sine of theta. So we can say our T3 sine of our theta minus the one that is pulling in this direction is our T2. So remember, T2 is changing direction. For this one it's going in this direction, for this other one it's going in that direction. So the free body diagram is isolated. So we are going to have something like minus our T2 should be equal to 0. We take the T2 the other side, it will be equal to, we have our T3 like that, sine of theta should be equal to our T2 like that. Now what do we have? We have our T3 sine of our theta should be equal to, we found T2 to be equal to 28.01 newtons, should be T2. T2 is equal to 28.01. Then we have two equations, both of them we don't know theta, we don't know T3. Now let's put them together. We have the T3 sine of our theta should be equal to 28.01. The other one is our T3 cos of our theta should be equal to, we have a 50 like that. So we have just gotten the two equations. Then what we are going to do is that as long as you just have one component on one side, just divide the one with sign, put it on top. So divide. So we are going to divide this one, divide this one, so that this one and this one cancels. You know that sine divided by cos is always equal to the tan of theta, should be equal to, if you want you can make T3 the subject of the formula, it's still okay, but this is also fast. So we are going to divide 28.01 divided by 50. This is going to give us a value that is equivalent to a 0.5602. Then we are going to say the theta should be equal to, we take the tan inverse of 0.5602. So our theta is equal to, we have the tan inverse of 0.5602. When we find the sine inverse of this, we are going to find that our angle is equal to 29.56 degrees. Upon finding the angle, you can get any of the equations. You can get this one, or if you want, you can get this one to find T3, since you now know the angle. So let's get even this one is okay. So our T3 is it sine? T3 sine of theta should be equal to, we have 28.01. We divide T3, we divide our sine of theta on both sides, sine of theta on both sides, so that our T3 becomes equal to 28 over the sine of our theta. Let's 28.01. Let's replace. So T3 is equal to 28.01 over the sine of our angle is equal to 29.26 like that, 26 degrees. So our T3 is equal to, we have the 28.01 divided by, we have the sine of the angle 29.26. This is giving us a value of a 57.31 newtons, like that. So that is how we solve that one. Let's move on to our next problem. Okay, so let's look at this question. So we have a light string ABCDE whose extremity A is fixed as a weight W1 and W2 attached to it at B and C. It passes around a smooth peg at D carrying a weight of 300 newtons at the free end E, as shown in the figure 4.17. If the system is in equilibrium, finds the tension in the portion AB, BC, and CD, and the magnitude of W1 and W2. So we have the answers provided. So how do we do this? So if you have one pulley system, like that, then you have a rope that is passing around the pulley system. The rule is that the string is inextensible, meaning to say if the tension one here is equal to, let's say, the same 300 newtons, it simply means to say even on this other side it will be equal to 300 newtons, as long as we have just one pulley system passing like that. So that means to say if your DE, which is the tension at DE, your tension at DE will be equal to, we are going to have the tension at DE is equal to, if this is 600, that means to say it will experience an upward, just as we have done 300 newtons up. So that means to say your DE, which you have already been given, we have a 300 newtons. Then even this other side, there will be a force of 300 newtons, like that, since it is just one string passing on a pulley like that. So that means to say we have already found the tension SC CD. So the tension CD is equal to so we can say T of CD should be equal to, we have 300 newtons, which they have given us as our 300. So that's the rule there. Then we are going to go to our next portion. So this one is very, very similar to what we looked at. So what are we going to do? So we have at least found the 300, so it's safe to begin with this point. So what we are going to do is this. So we have 300 there. We are going to draw our XY plane again. So taking this portion, we have the 300 going like that. So we have the 300. Then we have the tension. This was the middle part, so we are here. So this tension, we are going to just call it the tension of our BC, since they wanted, if you want you can say CB, it is still the same. Then what we are going to do is that, if we know that, we know to say from here up to here they have given us an angle of 120 degrees. That means to say if that is 120 and this whole thing is adding up to 180, you are going to subtract and you are going to find out to say this one will be 60 degrees, because 120 plus 60 will give you 108, and the straight line adds up to 180 like that. Then what we are going to get is that if that is 60, we are now going to resolve this force into its components. So the opposite side, let's say we are going to call this one as our tension. So it will be our tension of CD. Then we are going to say it will be the sine of theta. So this opposite side will be tension CD sine of theta. So just the opposite sides to the angle attracts the sine. Then the base shall be the TCD of we are going to say cos of our theta, like that. So this is what we have. Then as you can see, CD is acting in this direction, BC is acting in the other direction. If you want, you can just say CB. So CB is even better. CB. So we are going to say, so what else do we have? We have the weight number 2 like that. So we can begin anywhere. We can, if we want, we can choose to go up. So let's begin with our tension. Okay, let's begin with the summation of forces in the y should be equal to 0 because it's not moving. So we are going to say the one that is up is, as we can see, it is this one that is acting upwards like that. So we are going to say our t cd sine of our theta minus the downwards force, in this case is the weight, which is our weight number 2. A weight is can produce a tension, so weight number 2 should be equal to 0 like that. If we had something like T3, we could have equated T3 to this, but all in all, whatever tension is exerted on this part shall be equal to the weight. So we are going to say our TCD should be TCD sine of our theta should be equal to, when the weight goes the other side, it will be weight number 2 like that. We know that TCD is equal to 300. Then we have the sine of our theta is equal to 60 degrees, will be equal to weight number 2. So when we press 300 sine of 60, this is giving us a value of 259.81 like that, which should be equal to weight number 2. So this is a weight, so it's like that. So weight is a force, therefore it shall assume the newtons. If we check here, we are in the right track. We have 259.8. Then we have found that. So we have found the weight to be 259.81 like that newtons. Now let's find what our tension of BC is, or rather CB, since it's beginning at CB. So what we are going to do is that the one that is in the x direction, this one is moving in the opposite direction, which is our TCD. Our TCD is moving in that direction. So what we are going to say is that the summation of forces in the x direction is also equal to 0. So the force that we have is our TCD, then we have the cos of our theta minus the opposite side of this angle is equal to our TCB. So these are just forces, should be equal to 0. We take this, the other side, they are acting in different directions. So we have our TCD, cos of our theta should be equal to TCB like that. Then what we have is that the tension produced here is equal to, we have a 300 newtons, we have found it, 300 newtons times the cos of our 60 degrees should be equal to the tension in CB, which is the middle part. So we are going to have the 300 cos of 60. This is going to give us a value of 150 newtons, should be equal to our TCB like that. So TCB, one thing that you should know, is the same as TBC, which is equal to 150 newtons. So we have found the 150 newtons like that. So we have found the BC is equal to 150 newtons, which they have given us. This one is 259.81 newtons like that. We have also found the 300 here. So all we are remaining with is the weight down here and the tension at AB like that. So we are going to take this one again, draw another XOY plane like that. Now this one is attached to the wall, so it's going like that. Then what do we have? So we have one weight pulling down. So we have one weight pulling down like that, which is the weight number 1 like that. Then we have our CB, so our BC, which we found to be equal to 150 newtons. So remember, it's affecting both of them, just as we did for the last one. So now the angle is provided as 150 degrees. So from here up to here, we have been provided that this is equal to 150 newtons like that. So that means to say down here it will be equal to 30 degrees, since that is how the total straight line adds up to 180, like that. Then what we are going to have is that the opposite side will be equal to the t. So the opposite side will be equal to the tension here is, what is this side? This side is our BA. So we have our BA, but we can just call it AB, it's still okay. So we have our A, we have our B. So we have the tension AB. We can say opposite side will be the tension AB should be equal to tension AB. Then we are going to attach the sign of, we have the angle 30 degrees, like that. So that's our tension, like that. Then from there we are going to have so W1 is that. Then down here, since it is in contact with the angle, it will be TAB. Then we are going to say cos of our 30 degrees. So to find, so we don't have TAB, we don't have the weights, so we can first find TAB since we have the BC here. So we can begin with the summation of forces in the X. So we are going to say summation of forces in the X is equal to 0. Which forces? There is the force acting in this direction, which is our TAB. Then we have cos of 30 degrees minus the BC, the TBC should be equal to 0. Then what we are going to do is, let's take this the other side. So it will be our TAB cos of our 30 degrees should be equal to TBC. Then we know that TBC is equal to 150 newtons. Then we have our TAB. Then we have the cos of our 30 degrees. We divide by the cos of 30 degrees. We divide by the cos of our 30 degrees. So the TAB should be equal to, when we divide our 150 divide by the cos of 30 degrees, this is going to give us a value of 173.21 newtons. So let's verify. So according to this, that's the so that's the answer. TAB is equal to that. Then if you know your TAB, because if you know your TAB, you can now find the weight number 1, since this is affecting the y-axis. So we should identify for the y-axis, like that. So we are going to say the summation of forces in the y should be equal to 0. Which forces are those? So we have the TAB sine of 30. So we have our TAB sine of 30 minus the only downward force here is the weight. So minus the weight should be equal to 0. So we have weight number 1 should be equal to 0. So we are going to take the weights the other side. So our TAB sine of our theta should be equal to weight number 1. Let's replace. Our TAB is equal to 173 point. We have our 1. Sine of our angle is equal to 30 degrees should be equal to W1. Then we are going to say times. So 173.21 times the sine of 30 degrees. This is going to give us 86.6 newtons, which is equal to weight number 1, like that. So we have found our weight number 1. Let's verify. So weight number 1 is equal to 86.6, like that. So that means to say that's correct. Let's move on to our last problem. So it says the system shown in the figure below is in equilibrium. Determine the maximum value of W if the friction force on the 50 Newton block cannot exceed 15. What is the coefficient of static friction? So here what we are told is that finds the maximum value of W, the weight here. Then the other thing is that it is in equilibrium, meaning to say it's not moving. So what are we going to do? So what we have is this. So what we are going to do is that draw just the Cartesian coordinate, like that. Then draw all the forces. So we have the force downwards like that. So this is our W like that. It is pointing downwards like that. Then we have one force acting like that. Then there, what is there is that we have a 40 degrees here. So as you can see, we are forming a Z shape like that. So this is a Z shape. If we are forming a Z shape, it means to say if here it's 40 degrees, here it will also be 40 degrees. Now let's call this one as our tension, which is the force pulling the rope attached to there. So we are going now to resolve this force into its components. The opposite side will always be sine. So we are going to say T sine of our 40 degrees. Then down here we are going to have our T cos of our 40 degrees like that. Then what we are going to do is that now, as you can see, there is a force which is the object. Now it's not necessarily the object's weight that is pulling the object this side, no. So what we are going to say is that it will be equal to the frictional force is the one that is acting in the x-axis. Since this one has got the possibility of moving in this direction, so the frictional force will oppose the motion by moving the other direction. So this is what we have for that. Then what we are going to find the weight W, we are going to say, since this is in the y-axis, we are going to say summation of forces in the y is equal to 0. So the one that is acting upwards, we have the T sine of 40. So we are going to say T sine of 40 degrees minus the weight of the object is equal to, so these are the only two forces we have, should be equal to 0. So our T sine of 40 degrees should be equal to, we have a W like that. Now when we do that, we don't know what T is equal to, so that's why we go to the summation of forces in the X. It is also equal to 0 because it's not moving. Now which forces? We have the X component, which is our T cos of 40. So we are going to say our T cos of 40 degrees minus, we have the frictional force in the opposite direction should be equal to a 0 like that. So with this equation, we are going to find that we have our T cos of 40 degrees should be equal to the frictional force like that. So there are two ways of doing this. It's either you can divide these two, or if you can choose, you can just be able to find the value of T, because you already know that the friction they have given you is 15. You have the angle, so let's just divide, but even that one can work. So we have our T sine of 40 degrees should be equal to W. This other one is our T cos of 40 degrees should be equal to the friction like that. If we divide this, we are going to get this one and this one will cancel. Sine divided by cos, that one will be our tan of 40 degrees should be equal to the weight over the frictional force. So we have the tan of 40. So let's cross multiply to make W the subject of the formula. W times 1, it will be W should be equal to the tan of 40 degrees times the frictional force. We have been told that the frictional force is equal to, we have times the 15. So they have given us the frictional force to be equal to, frictional force must not exceed, if the frictional force on this must not exceed 15, meaning to say it is 15. So when we press our tan of 40 times the 15, this will give us a value of, we have a 12.56 newtons like that. So this is the maximum weight of the object. So with this simple procedure, you may have scored your 9 marks. Then here, what is the coefficient of static friction between the block and the table? So for this one, we are going to get the box like that and see which forces are acting on it. So already we have, it is experiencing a downwards force which is equal to its weight. So the weight which is equal to 50 newtons. Then since it is not entering the inside, so like this, since it's not moving up or down in that way, that means to say there should be a force that is causing the balance not to enter. That means to say that's our normal force, which is the contact force. So we have the normal force. So in this case, the normal force is equal to the weight. So the normal force minus the weight should be equal to 0. That means to say the normal force is equal to the weight if the weight goes the other side. So using this same principle, we are going to have, it is something like this. So we have the weight, we have the normal force, then we are going to say the summation of forces in the y direction is equal to 0. Then we are going to have our Fn minus the W should be equal to 0. So we have the normal force should be equal to, when this W goes the other side, it will be equal to positive W, or which will be equal to the normal force should be equal to, we have what is our weight. So the weight of this object is equal to 50 newtons. So our normal force is equal to 50 newtons. Then we know that the reason why we have found the normal force is we know that the frictional force is equal to the coefficient of static friction times the normal force. Then we can just replace. We know that the normal force is equal to 15, should be equal to, we have our mu s times the normal force has been found to be 50. We divide over 50 on both sides over our 50 on both sides. We are going to find that our mu s is equal to, we are going to have our 15 divided by 50, which is going to give us a 0.3, like that. So this is our coefficient of static friction. Thank you very much for watching. Hope you would like, subscribe and share for more. See you in the next tutorial.